As usual, I like to start a new concept by reviewing and looking at where we've come from. So let's look way back at the beginning of the year, coming out of pre-calculus and into calculus. You were able pretty functionally to graph a curve. In this case, I've graphed the sine function, y equals the sine of x. And in standard position, I can label the roots as 0, pi, and 2 pi. You also, from a polynomial, and let's keep it simple, perspective, I could graph the quadratic y equals, say, 1/4 x squared. Then we spent a good part of the first semester looking at the derivative and applications of the derivative. Specifically, for example, if I want to know what is the instantaneous change, not the average change, but the instantaneous change at, say, pi over 3, I could calculate the derivative, plug in pi over 3, and find the exact slope or rate of change at exactly that point, pi over 3. Same thing on a polynomial function. I could certainly plug in, for example, -4, take the derivative of the function, plug in -4, and it would tell me exactly the slope of that line. Then we moved on from there and looked at another scenario, which was the area between a function and the x-axis. And in this case, remember, we were able to calculate the antiderivative of, for example, sine x. And in this case, I'm looking for the area between 0 and pi on the x-axis. So I could say on the interval from 0 to pi, the antiderivative of sine x, using the first fundamental theorem of calculus, it would tell me exactly the area or the value of the area on that interval. Let's go ahead and do that. Sine x, the antiderivative is negative cos x, which still has to be evaluated from 0 to pi. And so second fundamental theorem of calculus, I'm going to pull the -1 out. We get the cos of pi minus the cos of 0. That's negative. Cos of pi is -1 minus cos of 0 is 1. And so the whole thing equals -2, which is a positive 2. So the area between the sine curve and the x-axis from 0 to pi equals 2. On the polynomial, we might as well be thorough. Polynomial function, let's do the same thing, only this time let's look at between let's look for the area between 0 and 4. So again, we're looking for this area using the antiderivative. So the interval from 0 to 4, the antiderivative we're looking for is that of 1/4 x squared dx. Well, that equals 1/4 times 2x, which has to be evaluated between 0 and 4. And so the area is 1/4 times 2 times 4 minus 2 times 0. 1/4, 8, take away 2 is 6. And so the area marked here on my diagram is equal to 3 halves. So probably a review you didn't necessarily need, but definitely a review I wanted to make, because now I want to take the concepts that we've developed here and look for the area between two curves, which means that we can expand what we already know about area, which is between some function and the x-axis, to be described as an area between one curve and another curve. So let's sketch in some sort of random curves. So say the top curve here is f and the bottom curve is g. If I'm given some x1 and x2 value, then I can calculate the area between f and g using the same methods that I used before. Basically, if I know that the area between f and the x-axis is the antiderivative from x1 to x2 of whatever the function of x is. And I take away from that the part of the area that is the g, between g and the x-axis. So let's sketch that in with color. So the antiderivative, or the area calculated between f and the x-axis, would be shown here. But to find the area between f and g means I want to subtract out the part that is the area between g and the x-axis. So between x1 and x2 on the function g of x dx. But we know that anytime I have the same area, or the same bounds of integration of one function, take away another function, that can just be rewritten simply as the antiderivative from a to b, I'm going to generalize it at this point, of f of x minus g of x dx. So that looks like a good place to start with an example. So we want to find the area of a region that is bounded, and I'm going to sketch it real quick. It's bounded by the curve x squared plus 2, and the line at 1 minus x, and the x equals 0, or the y-axis, and x equals 1. So on the region between x equals 0, x equals 1, there we go. So we want to find the area of that region. Well, that would be easy enough, right? We want the antiderivative on the interval from 0 to 1, so first handling the direction on the x-axis, and then we want to take the bigger function, which is f of x, and we're going to subtract from that the smaller function, which is g of x. So that's on the interval from 0 to 1 of x squared plus 2, and I'll put parentheses just to be safe, minus g of x, which is 1 minus x. So that's from 0 to 1, x squared plus 2 minus 1, well, there's no reason to write that out 3 times. X squared plus 2 minus 1 is 1. Minus x is plus x dx. Oops, dx. And I could rewrite that to make it pretty, but I don't really see any reason to. I'm going to go ahead and take the derivative. So we have, or excuse me, the antiderivative. So I have x cubed over 3 plus x squared over 2, and I want to evaluate that from on the interval from 0 to 1. So the 0 is just going to zero out, so all I have to worry about is the first part. So I have 1/3 plus 1 plus 1/2, which is 1, nope, that's not right, which is 2 plus 3 plus, still not right. Sometimes arithmetic is hard after you've done the calculus, right? This is 3 times, oh, I was right. 3 times 2 is 6, 1 times 6 is 6, and 1 times or 2 times 3 is 6, all over 6. So 6, 8, 9, 10, 11, that'd be 11/6 would be the area of the region between these two curves. And the y-axis and the line x equals 1. I could sketch it this way. Seems like a good time to do another example, because this time we want to look at something a little bit more complicated. So let's find the area of the region that's bounded by the graphs f of x equals x cubed minus 3x plus 2, and g of x equals x plus 2. Now in this case, I'm not giving you a y-axis or a location on the x-axis as a boundary on the right or the left, because these two graphs actually intersect each other at 3 different points, which give us the boundaries on which we're going to calculate the antiderivative. So first, let's figure out where these two graphs intersect. And of course, where they intersect would be at the point x cubed, or the points x cubed minus 3x plus 2 equal to x plus 2. So I have x cubed minus 4x plus 0, well, I'll write it down, equals 0. So x cubed minus 4x equals 0. Pull out an x, and I have x squared minus 4 equals 0, difference of two squares, x times x minus 4, minus 2 times x plus 2. And so I know that the boundaries, or the intersections of these two functions, are at x equals 0, -2, and +2. So if I were to sketch these out real quick, I'm going to start with the line. So the line, the y-intercept is at 2, and the slope is a simple slope of 1. And I've got a cubic function, it's positive, so I know that based on the parent, it's going to be some form of that, but I know that it's going to be loopy because I have a linear and a constant term. And so really what I have is at x equals 2, I have a point of intersection, and at x equals -2, I have a point of intersection, which happens to be right on the axis. And I want to find the area between these two functions. And now that I have my picture sketched out, I can see that I have a little bit of a dilemma. And that is, remember, to find the area between these two curves, I want to take the larger function and subtract from it the smaller function. But notice that one function is larger on the left-hand side of 0, but smaller, the same function is smaller on the right-hand side of 0. So f is both less than and greater than g, depending on where I look at it. That's not that big a deal. We're just going to take two different intervals. We're going to look first on the interval from -2 to 0 of f of x minus g of x. And we want to add to that the area, or the interval from 0 to 2, the antiderivative of the got a little tongue-tied. There's a lot of lingo going on right now. The antiderivative, or calculate the area by finding the derivative on the interval from 0 to 2 of this time g of x minus f of x. And the rest of it's all just pluggy-chuggy. The antiderivative from -2 to 0 of x cubed minus 3x plus 2 minus g of x, which just means sign changes, minus x minus 2 dx, plus the antiderivative from 0 to 2 of g of x, x plus 2 minus f of x, which means sign changes. Okay. But all of this just simplifies to x cubed minus 4x dx plus 4x minus x cubed dx. Calculate the antiderivative. I have x to the 4th over 4 minus, well, this is going to be x squared over 2, so the 4 reduces to give me 2x squared, which has to be evaluated from -2 to 0, plus I'm going to have the same thing here. So I'm going to have a positive 2x squared. I should probably group this a little bit better. Positive 2x squared minus x to the 4th over 4, which needs to be evaluated from 0 to 2. So I have, well, 0 works because these just zero out. So negative 2 to the 4th power, 2, 4, 8, 16. But it'll be positive. 16 divided by 4 is 4. Minus negative 2 squared is 4. Times 2 is 8. Plus, and it works in the opposite direction this time. Instead of having the first half disappear under the influence of 0, now the end is going to disappear. So again, 2x squared, 2 to the 2 squared is 4, plus times 2 is 8, minus 4. So I have minus 4 minus 8, 4. So a negative 4 is a positive 4, plus 8 minus 4 is another 4. And so the area marked here in the blue is equal to 8. All right, so let's recap. When you want to find the area between two curves, first thing you want to do is find out where the two curves intersect, because the area between the curves is going to be wherever between the first and the last intersection of that curve, of those two curves. So we'll use systems of equations by whatever method to calculate the locations where these curves intersect. Then we're going to use our knowledge of graphing, which should be pretty extensive by now, to sketch out a little picture of what I'm looking for. And then we want to set up our antiderivative based on the picture that we see. And then pluggy chuggy, find our area. All right, so now a comment about graphing calculators. This curve was pretty easy to sketch. Both of them, obviously the line and the cubic, were pretty simple to sketch. It was pretty simple to find the points of intersection and to set the problem up. On a problem like this, I would expect you to do it by hand as well. But many of the curves you'll be working with in this unit are not as simple as this. And so I'll be allowing a lot more liberal use of your graphing calculator in your actual work. Notice I've sketched this curve. Also notice I didn't sketch it correctly. I didn't see the root here. I didn't acknowledge the root. I didn't even look for it, so I didn't anticipate one being there. All I needed was to know that f was greater on the left-hand side of the y-axis and less than on the right-hand side of the y-axis, so that I could set up my integration. Also, finding the points of intersection, super duper easy in this case, not always going to be true. So if you notice, I'm using the trace function. I can see that my x value is at 2 on the left-hand side. If I trace along my curve, I can see that they also share an intersection point at x equals 0. And then continuing all the way around, I can see that the last point of intersection is at x equals -2. So feel free to use your calculators, sketch a graph, sketch it out on your paper from your calculator. If you're given a problem on a test, I'll either allow for you to use your calculator, or I'll give you a problem that's very simple to do by hand.